Hello and welcome to another section of Introduction to Astrophysical Fluid. As promised, in this session we will discuss or we will start discussing a new topic, that is the effect of rotation in astrophysical systems. So in many astrophysical systems, rotation is very much important because first of all they are the prominent effect which can be seen by direct observations. Okay, and how to see, how to see the direct observations means you can actually see, for example, for sun you can see really the images which can give you the evidences of rotation. For distant stars or for distant objects where you cannot see directly, then you have several other evidences. One evidence is that you can detect rotation by the virtue of the angular momentum associated with them. For example, for a distant accretion disk, for example, or a spiral galaxy. Okay, then there are several methods by which you can calculate the angular momentum associated with the system, and by using that you can actually confer that the system is undergoing some rotation. And even very interestingly, it is true that even there are other techniques other than this angular momentum. There are other techniques by which you can actually also detect rotation. Okay, so that is totally a different topic. So if you are interested, you can search over internet. Now, what are the typical systems, typical astrophysical systems where we can see, clear evidences of rotation? First, we have already discussed the case of accretion disks, right? Then something like that, but in a larger scale, this is called the spiral galaxies. So the galaxies, for example, so Milky Way, for example, okay, it has something a spiral type of disk. It has a, shape like a spiral disk type of thing, and it rotates. Okay, and also, so these two were mostly the disk type of rotation. Okay, disc shaped things which are rotating. Now there are coming coming the problem of the rotation of the stars, where you can see the almost spherical objects are rotating. And the same thing for the compact objects, for example, the white dwarfs, the neutron stars, including the black holes. The black holes have also clear evidences of rotation. Okay, so for example, one question is that how to detect the rotation of the black hole or the spin rate of the black hole. So there are very interesting works on that. You can also search for that over internet. Now, for all these systems, the inclusion of the rotation is essential. Of course, if the system is very much massive, that means compact object, black holes, then we actually have to take the gravitational correction due to general relativity into account. But in the scope of this current course, we will just do something where we don't need to include the general relativistic effect, that means the space-time curvature. Okay, that we will not consider in this course. So we will do something where simple classical rotations are needed. Okay, now as we already have discussed while discussing while discussing the equations of the perfect fluid, and then discussing the Newtonian fluids and how the velocity gradient can have an unnecessary part other than the true viscosity part. Okay, so that we have seen, and we have actually concluded that there is a part of rotation which also can give you a velocity gradient, but this is not a velocity gradient which where the viscosity plays any role, right? That we have already seen. Okay, So, and then also we introduced two types of rotation. One was the solid body rotation, another was the differential rotation. So the solid body rotation is nothing but a rotation where the whole body is moving with a constant angular velocity. The linear velocity can be different, but the angular velocity omega should be a constant. Okay, so remember that omega times r gives you the linear velocity in the cross radial direction. Okay, so for this type of motions in general. Now for a solid body rotation, you can actually see that you have let's say if you are just assuming concentric shells like this, or concentric cylindrical shells, then actually they have some so they have the linear velocity gradient, but they don't have any angular velocity gradient. Okay, on the other hand, for differential rotation, both the angular velocity and linear velocity, they vary in space, and so that we have a linear velocity gradient as well as an angular velocity gradient. And when differential rotations are coming into play, then what happens that the viscosity between two concentric layers, they are actually, this becomes active because I mean in rotation the main role of viscosity is to prevent the relative rotation of one layer with respect to the other, right? So if both of them are rotating in the same rate, then the viscosity effect would not work or would not be activated. Okay, but in differential rotation this is not the case, so viscosity should play. Now it is true that in usual fluids, very rarely solid body type of rotation actually is visible. Okay, because of there are so many things, compressibility, this type of thing. But if you are just taking a liquid, for example, which is fairly incompressible, so okay, then differential rotation also starts to appear in the very beginning. Okay, we will see that after some time actually it can be decayed, okay, or actually decays. So what happens, let us just take the concrete example of from our everyday life. So let us take a bucket full of water and the bucket is rotated suddenly. Okay, just try to imagine the picture. So if you have a bucket like this, okay, a cylindrical bucket, and then you just put some torque, okay, on the surface of the bucket like this, and you want it to rotate. So the first thing which rotates is the surface of the bucket. Okay, because you give the force here. Okay, you give this is a shear as well, this is a rotational shear, right? So this gives you the rotation, but the rotation starts from the surface, but the water which is very near to the axis of the bucket and far from the walls, this water is yet to start its rotation, right? So if you can easily understand that at the very initial point, the angular velocity near the wall is greater than the angular velocity near the axis of the bucket, right? So this actually creates an effective differential rotation. Okay, then viscosity comes into play to counter, to how to say, to stop and rather to resist the relative rotation between two concentric layers. And so for example, the fast rotating layers will try to move the adjacent slow rotating layers move faster, and vice versa, and finally they end up by making a compromisation. And then what happens that the relative angular motion actually stops, and that leads to a state where all the water will finally spin with a constant angular velocity, and that is nothing but the angular velocity of the bucket itself. And at this point, the whole system will rotate like a rigid solid body, and this is actually known as the solid body or rigid body rotation, right? So here we see that when viscosity comes into play, it basically transforms a differential rotation to a solid body or rigid body rotation. Okay, but it of course takes time. So in astrophysics, where if let's say by some observation or by some direct or indirect observation, if we have evidence or if we gather evidence that some systems do not rotate like a solid body, for example, then what can be the possible explanation for that? Why? There can be two possibilities. One is that the viscous forces, they may not have enough time to develop and establish a solid body rotation. That means if the system is rotating very much fast. Okay, so that is the case for a fast rotating star. That we will not discuss here in detail, but just for your information. Another possibility is that the system, for the system, the viscosity has time to develop, but the system contains some sustaining mechanism which maintains the differential rotation. And now the question is that where can we see this type of thing? Okay, so for that, let us start by taking a very simple example which we have already studied in detail. That is the example of accretion disk, and along with that we will say something very similar, that is the case of spiral galaxies. So this is these are two axisymmetric rotating entities in astrophysics. Okay, axisymmetric means that they have a direction or axis of rotation, and in this so the properties along the direction of the rotation is different from the properties perpendicular to the properties in the direction perpendicular to that direction of rotation, but in the plane perpendicular to the direction of rotation, it does not matter in which direction you are in. So all the azimuthal directions, or the, so if you just consider the how to say, the cylindrical system, then basically the system will have a z, the system changes from z cap direction to the r phi plane, but in the r phi plane, okay, it does not depend that where, how much your theta is. You can also depend on r. Okay, then you can actually go from the inner concentric cylinders to the outer concentric cylinders, or vice versa. But on one cylinder, okay, so the system does not depend on the choice of depend on the azimuthal angle phi. Okay, so whenever we talk about axisymmetric system in cylindrical system, del phi should be equal to 0. Sometimes we also say del theta. Okay, it depends on the convention which we follow. Either we take r theta z, or we take sometimes take in some literatures rho theta z, or sometimes we say r phi z or rho phi z. Okay, so this type of conventions all are present. So now we try to analyze a bit more in detail the case of the rotation and how the rotation mechanism basically is developed in an axisymmetric rotating entity like an accretion disk. For that, we recall the R component of the Navier-Stokes equation for the steady flow of such a system. If you remember the basic accretion disk system, we had a very small but non-zero radial velocity, but very small. the velocity was predominantly in the cross radial direction, that is in the azimuthal direction. Okay, and we said that the system was a steady system, and sorry, the system is axis symmetric system, so del theta or del phi would also vanish always. And then we also said that the system has the system has some viscosity, and that viscosity was responsible for causing the small radial inflow of mass, if you remember all these things. Okay, so just if we also remember that the main equation of dynamics for the accretion disk that came from the theta component of the cylindrical, of the Navier-Stokes equation written in the cylindrical coordinates. For the r and phi, z components, we had other information. For example, for z, using the z component, we thought we obtained the condition for thin disk, and using that one, actually we obtained from the r component of the Navier-Stokes equation the Kepler's criterion, right? So here we will actually follow the same methodology. Okay, so here you will see that the r component of the Navier-Stokes equation looks like this, because the we are just considering a steady state motion of a motion of an accretion disk, so that we cannot say that the system does not have enough time for the viscosity to be developed. But remember, the steady state system is just gives del t is equal to 0. But for our case, for simplicity, we also assume that Vr is very small, so Vr can also be practically 0, and del theta is 0. If we assume all these things simply in cylindrical coordinates, the r component of Navier-Stokes equation becomes minus v theta square by r is equal to gr. Gr is nothing but the radially acting, okay, the gravitational acceleration, minus 1 by rho del p del r. Okay, now you see that this is nothing but the centrifugal force. If you are in the in the frame of reference of the rotating system, or if you are just seeing the system from the laboratory frame of reference, then this is nothing but the centripetal force required to maintain the rotation. Okay, and this is the gravitational part, and this is the pressure gradient force. So if you remember that for accretion disk and spiral galaxies which are thin, okay, we can actually, or in practical, neglect the pressure gradient force, okay, just a minute, to the gravitational force, or the the net acceleration due to the pressure gradient force will be negligible with respect to the gravitational acceleration. Okay, because the ratio will be, just check your old notes, okay, where we discussed the accretion disk, the ratio of the two will be simply of the order of h square by r square, and for a thin disk this is negligible. So just a point, this can be an interesting study to see that how this type of equation, how this ratio becomes for a non-thin disk. Okay, so in a thin disk we are getting rid of this term, and we will say that the pressure gradient force is no longer necessary for this balance equation. So we will say that it is effectively the gravitational part, gravitational acceleration, which provides the necessary centripetal force or centripetal acceleration. Okay, so minus v theta square will be by r will be exactly equal to gr. Okay, and that then you can just say that just taking the mod, that v theta by r, so if you just divide both sides by r, so it will be v theta square by r square is equal to gr by r. So you know also that GR should be radially inward directed so that it is an attractive one. Otherwise there is no meaning of rotation in this case. Okay, and so we have to just make the for checking for how to say that, for investigating the relative importance, we will just take the modulus of this, and then this will be exactly equal to V theta by R is equal to the mod of this. Okay, this will be exactly equal to minus of minus V theta square by R, so it will be V theta square by R. So V theta by R will simply be equal to root over modulus of GR by R. Right, you just divide both sides by R and you take the mod, so there it will be plus, and then you have this. And what is this? This is nothing but our well-known Keplerian motion. So a Keplerian motion basically gives a clear evidence of a sustaining differential rotation, because V theta by R, so if you again remember that R omega is equal to V theta, so omega is something which is depending on R. Okay, as we all know that GR is not linearly depending proportional to R, so there is no chance that there will be one R and there will be one R which will cancel and gives you something which is independent of R. So the only possibility is that there is an R dependence. Okay, so we have a differential rotation, but remember, this does not say that in these systems viscosity is not present. In general, viscosity is present in such a system. But what happens that the role of the viscosity is just to induce a slow radial inflow of the mass rather than leading to a solid body rotation. The question is that, so if, in other words, the question is that, if you, for example, if you go to this equation, you will see that there is no term from viscosity, and that's because of the simple fact that VR is so small that the viscosity term, which should be some nabla square or Laplacian VR times some coefficient of viscosity, will be very, very small. And that's exactly the case where we are talking about the neglecting the viscosity for at least for this rotation purpose. That means the contribution of viscosity to counterbalance the net centripetal centrifugal force, or to provide the necessary centripetal force, whatever. Okay, they are equivalent pictures. This is negligible. Okay, so viscosity is there, but viscosity's only role is to induce a slow radial inflow, and that can be seen when you write the governing equation for the evolution of V theta. So that is the theta component of the Navier-Stokes equation. You should remember that. Okay. Now that was the case for the accretion disk or spiral galaxy. Now what happens if we consider the case of a slowly rotating star? Now in this case, one part of the pressure gradient, they balances the gravity. Okay, so in the previous case, the pressure gradient force was negligible. The centripetal force was provided, centripetal acceleration was provided by the gravity here, and that led to the Keplerian motion, thereby sustaining a differential rotation. Here, one part of the pressure gradient balances gravity, and the other part, so pressure gradient first of all is no longer negligible at all, and actually this is the most dominant part, so that one part of this balances gravity, and the other part, along with the viscosity, counterbalances the centrifugal force. Now the question is that when I am saying along with the viscosity, does it mean that this nabla square V? Well, this is also not correct. Okay, so actually this is not the normal molecular viscosity or Navier-Stokes equation viscosity in direct sense, which is responsible here, but there is another thing, it is called turbulent viscosity, which I will talk when I will introduce the general properties of fluid under turbulent conditions. Okay, then I will talk about the turbulent viscosity. So turbulent viscosity is an equivalent viscosity uh, coming from the virtue of the turbulent motion of the fluid. Okay, and this viscosity basically reduces the this viscosity basically reduces the differential rotation, and then finally leads to the system to a state of solid body rotation. Okay, now turbulent viscosity, just for your information, is very interesting, and it can be it is actually in general anisotropic. Okay, so turbulence viscosity is anisotropic, and when this anisotropy is very strong and is non-negligible, then actually the differential rotation is not transferred or transformed into a solid body rotation, and that is exactly the case of our sun. Okay, of our famous star sun. So every time we will see something in sun, that will create a very important aspect for us, or rather for our astrophysical knowledge, because sun is our point of reference in some ways. Okay, so for sun, differential rotations are prominent, and actually, just to tell you that I already discussed about that sometimes this differential rotation, the signature of differential rotation, including the spatial distribution of the angular velocity, can actually be obtained using helioseismology, that is the physics of the oscillation of sun. Okay, so radial and non-radial modes. Okay, so using this, actually people have obtained some spatial profile of the angular velocities, and actually it is shown that near the poles the sun moves very slowly, and near the equator it runs fast, it rotates faster or spins faster. Okay, and the discrepancy in the angular velocity or the angular speed is by 10%, and actually it's sometimes it's more than 10%, so this is non-negligible. Okay, so this was the case where you can exactly see clearly differential rotation. Okay, and that is not the case for the slowly rotating stars, where the turbulent viscosity is approximately isotropic. That means if it is the turbulent viscosity is let's say is represented by some matrix, okay, by some tensor, okay, 2 by 2 sorry, second rank tensor, then its off diagonal terms will be then the matrix will be symmetric. So something like tau xy will be equal to tau yx, for example. Okay, so and then not only that, then tau yz will be equal to tau zy, and not only that, tau zx will be equal to tau xz. Okay, and not only that, finally you can see that these off diagonal terms and the diagonal terms will be almost equal. Okay, not only those things, but this will be almost equal. That means, and the diagonal terms will also be very close. That means, let's say tau xx, tau yy, tau zz, this type of thing, they will also be very close. Okay, and only then you have this turbulent viscosity can be very nearly isotropic. Okay, so we will come to that point. So you know from your knowledge that turbulence, I mean the viscosity comes from the off diagonal part of the pressure tensor. So what about turbulent viscosity? That I will discuss later. So just for your information, if this is nearly isotropic, which is the case for slowly rotating star systems, then any differential rotation actually decays with time, thereby leading to the final state of a solid body rotation almost. But this differential rotation can be sustained if the turbulent viscosity itself is strongly anisotropic, and that is the case for the sun. Now, there is a very important point. All types of differential rotations are not self-sustaining. Okay. And what is the reason for that? Well, it depends on the dynamics and the structure of the system. So a general analysis or general answer for this question is not very easy to obtain. However, by doing some very simple analysis, we can actually determine some condition for which a fluid is stable under a differential rotation. That means a fluid is already moving with a spatial gradient of angular velocity. Now if we part out the system, would the system try to get back its original configuration with the differential rotation? Let's say the perturbation is done in such a way that the differential rotation state is made to tend towards a solid body rotation. Now would that be would that be a stable condition, I mean stable state? That means would the system try to bounce back to its initial position condition, I mean initial state, or not, or it would further move away? Okay, so if it would try to get back its original position or original state, then the fluid is called stable under a differential rotation. That means the system loves, the system likes, okay, or rather the system prefers to be in a state of differential rotation. For simplicity, here we take an incompressible fluid which is subject to a differential rotation around an axis of symmetry. Okay, so now you see, so this type of disk is there, and we are just taking two concentric rings. One is at R1, another is at R2. Of course, R1 is less than R2, and we consider the fluid, I mean, which is anywhere in this axisymmetric case, and the fluid is only moving in this theta cap direction, so it has only azimuthal motion, so VR is 0 practically. This is the case for accretion disk as well, and V theta is the whole velocity. Okay, so you can see that this ring is moving with linear velocity v2, and this ring is moving with linear velocity v1. Of course, both of them are just rotating like this. Okay. Now, in our treatment, here we neglect the effect of body force, that is the gravity, for the sake of simplicity. And one interesting study can be done to see what the effect gravity gives. Okay, so anyways, so we now consider two volume elements of equal volume, that means dv dv. Well, two volume elements actually have the same meaning, that both have dv and dv. Okay, at it should be at R1 and R2. I'm extremely sorry. At R1 and at R2. Now, since the system is only considered to have a cross-radial motion or azimuthal motion, then UR is 0. And again, writing the Navier-Stokes equation in cylindrical coordinates because of the axis symmetry, we have finally dVr dt. So ddt is nothing but the material derivative. That means we are now concentrating on a fluid element or fluid particle. Okay, so dVr dt minus v theta square by r is equal to 1 minus rho del p del r. So the acceleration of the fluid element is due to two things. One is the centripetal acceleration and one is the pressure gradient force. Okay, and then okay, so this is the net acceleration. Okay, so now the question is that how should it look like for our case? So of course you can see that for our case this will simply be 0 because Vr is 0, and you will say that this the total centripetal acceleration is provided by the pressure gradient force. That is the conclusion from this component. What is the conclusion coming from this component? I'm sorry. Coming from this component, we simply say that this is the theta component or the cross radial component. We have dv theta dt plus vr v theta by r is equal to 0. All the other terms are 0, either because they are depending on theta or they contain they're just depending on theta or they have other negligible things. Okay, so now Vr is 0 makes this thing again simpler, which simply gives us dv theta dt is equal to 0. So that means the linear velocity of the fluid element, okay, this is ddt, so the linear velocity of the fluid element does not change with time. Okay, is this clear? So the velocity, the linear velocity with which one fluid element is moving is constant. Again, Vr is equal to 0. What is the meaning of that? That means ddt of r is equal to 0, right? This is the simple meaning of this. And if we combine this one and this one, then we can write that ddt of r v theta is equal to 0. So for a particle, not only v theta, not only r, but r times v theta is also constant in time. And this is nothing but, you know, that this is the mass density of the angular momentum. So this is angular momentum per unit mass. We call this h, and this is a constant of along. So this is the constant along the trajectory of a fluid element. Okay, so this is a Lagrangian invariant because we are now talking in terms of the Lagrangian derivatives. Okay. Now, what is the kinetic energy density of that particle? That should be, what is the kinetic energy density at some position, at any position? That is the half times the density times the velocity square, and the velocity means only v theta. So it is nothing but is equal to half times rho h by r whole square, because v theta is nothing but h by r from this relation. So now that if we just think that we have concentrated on two fluid elements, one is here, one is there, or you can just think here and there, and we calculate, so before doing any change, we calculate the total kinetic energy of those two fluids, two fluid elements, and they will be nothing but half rho times h1 square by r1 square times their volume dv plus half rho times h2 square by r2 square times dv, their volume. Simple. They don't have any other force due to potential or body force that is neglected over here. So the only energy is the kinetic energy. So now you can simply say that we make an interchange of those two fluid elements. So now we just pick the fluid element which was primarily at R1. Now we put this at R2, and that which was at R2 now will be put at R1, and where R1 is less than R2, once again, if in case you forget. Okay, then what happens that at the new position, they will have the total kinetic energy, that is E prime, which is equal to half times rho h2 square by r1 square plus h1 square by r2 square dv. Now look, these particles, they are just peaked and they are put in a new position. So they will come with their instantaneous angular momentum density, okay, before the perturbation. Okay, so and we will see that if we just, they are just peaked and they are just put in the new positions, would they suit the new position or not? That is the question. So if we simply pick them from their original positions and swap between them in terms of the position, but they are always associated with their original angular momentum, then the question is that would that system be stable? How would the system respond? Of course, the system will be stable, one can easily understand, if E prime is greater than E, because the system, if the systems, if the final energy is less than the initial energy, the system would always try to go to the final state and then it will try to move further away, okay, from the initial state. But only if the new state has an energy which is greater than that of the original state, then the system would try to bounce back to its original state, and that is the stability. So for stability, here this is a bit, I mean, this can be confusing sometimes, that here when we talk about the stability, that means the stability with respect to the differential rotation. So for our system, the stability will be attained if the energy in the final state would be greater than the energy in the initial state, because we want the system to get back to its initial state, and that should be the state with less energy. And if it is true, then you can write that this is simply equivalent to writing h2 square by r1 square plus h1 square by r2 square is greater than h1 square by r1 square plus h2 square by r2 square. Okay, and then I take this all the terms with h1 square in one side and all the terms with h2 square on the other side, and we have h1 square 1 by r2 square minus 1 by r1 square is greater than h2 square times 1 by r2 square minus 1 by r1 square. Now since r2 is greater than r1, then this term is smaller than this term, so this is a negative thing, this is a negative thing, these are positive because they are squares. Okay, so I mean, when you just say that some negative things are cancelled from both sides, then their relation would also inversed, would also be inversed, and then this would actually leads to the condition that h1 square should be less than h2 square, and that is the condition for stability. Whereas the opposite condition, that is h1 square is greater than h2 square, will be the case for instability. So if you write in terms of, for example, omega and theta, so what was h, if you remember, so h1, so h was nothing but r v theta, right? So another alternative way of writing this is that, so just I can write over here if you want, that this is equivalent to writing, okay, so for instability, actually maybe it is good that I write for stability. Okay, yeah, sorry. So for stability, what we need is h1 square is less than h2 square, right? And that simply says that, what is the definition of that? r1 square r1 square v theta 1 square will be less than r2 square v theta 2 square. Okay, now what is v theta? So once again, v is nothing but, v theta is nothing but r omega. So if it is r V theta 1 R1 omega 1. So that would simply be R1 to the power 4 omega 1 square would be then less than, or rather I just use this omega. Okay, omega 1 square, then R4 omega 2 square. Okay, so if R2 is greater than R1, then this condition, this quantity should be greater than this quantity. So a differential way, if we just change now those two volume elements between two concentric layers, okay, which are infinitesimally close to each other, then an equivalent way of writing this is, because this is true for any layers, ddr of omega square r to the 4 would be greater than 0. So this is the, sorry, is greater than 0. So this is known as the release criterion. This one is known as the release criterion for stability. Okay, this one. So sometimes we say this release criterion of centrifugal instability. Centrifugal stability, of course, this one. Sorry. This is the release criterion for centrifugal stability. And this one, the opposite condition, is known as the release criterion for centrifugal instability. And really, in the year 1917, for the first time, he derived this one. Okay, so you see that here in this lecture, by a very simplistic condition and simplistic analysis process, okay, we have not done much formal things, okay, just, and for very simple cases, axisymmetric, only azimuthal flow is there, steady condition, incompressibility, using all these assumptions, finally what we concluded that not every differential rotations they are auto-sustained or they are self-sustained. So if the Rayleigh's stability criterion is satisfied, then once a differential rotation is established in a system, it will be there. Okay, it will be there, it will not be decayed. Now if the differential rotation is not sustained, then what is the fate of that? Then we can assume with time it will be, then this is the criteria for instability, right? And that means the differential rotation is not sustained. That means the fluid does not prefer to be in a state where different layers are moving with different angular velocities. And then what is the fate? What is the destiny of that system? To be in the state of solid body rotation. Of course, Sun is not like such a system, because in Sun we have sustained differential rotations. Okay, in the next lecture we will discuss a bit more about these rotations, and also we will try to understand how such a system can be studied from a non-inertial frame of reference. Okay, thank you very much.